Alright, today we're going to go over the awesomeness of thermochemistry. Thermochemistry is the branch of chemistry concerned with quantities of heat evolved or absorbed during chemical reaction. The temperature is the degree or intensity of heat present in a substance or object, especially expressed according to a comparative scale. A kilojoule is equal to 1,000 joules. The system and its surroundings. The system is part of the universe. The surroundings are everything else in the universe. For example, I am a system, and while I run, I release heat into the universe. The system and surroundings balance with each other to set an equilibrium. Heat capacity and specific heat. The number of heat units to raise the temperature of a body by 1 degree is heat capacity. The heat required to raise the temperature of a unit mass of gram substance by a given amount, usually 1 degree, is a specific.
In chemistry, heat flow is where heat is transferred or exchanged from one place to another. So recently I was able to capture a picture of Gene during one of his morning jogs. In this case, Gene is his system and everything else is the surrounding. Since Gene is warmed up from the jog, he is relatively warmer than everything else. In detail, Gene bears more heat, and as a result, heat from him is transferred to the surroundings. This is called an exothermic reaction, where heat is transferred from the system to the surroundings. Next, we have here a picture of Barbie surrounded by candles. Barbie in this case is the system, whereas everything else is the surroundings. Since Barbie is cold, the heat is transferred from the candle flame to her. This is called an endothermic reaction, where heat is transferred from the surroundings to the system. Now if Barbie was any closer to the flame, she would absorb too much heat and melt. This brings us to our next standard, which is how energy works in changes of state. To begin with, here we have a solid man who has a definite shape and definite volume. His particles are very firm, such that of a solid, and are vibrating in place. However, when the sun comes out and increases the temperature, the particles in him start accelerating in motion because they absorb the heat. In detail, the increase in temperature increases the motions of the particles in him, and soon he becomes a liquid fluid as a result of melting. The liquid's particles are slightly looser and has no definite shape, but has definite volume. The intermolecular forces that binds the solid are no more, as there are too much thermal energy that loosens these molecules. But as the sun gets more intense and the temperature increases, the particles absorb more heat and energy, causing the molecules to increase in motion. Thus, it evaporates and becomes a gas. The gas man bears fast-moving particles that move freely and randomly. In fact, the intense temperature level accelerates these molecules to a degree where they have no definite volume and no definite shape. Furthermore, the same concept of heat and energy applies to the opposite change of state as well. For example, using grass as a medium, the gases surround it at a normal temperature. However, as the temperature decreases, the motions of the molecules slow down and heat is lost. When these molecules decelerate, they start binding to one another and become a liquid through condensation. As the temperature further decreases, further heat is lost and the motions of the molecules decrease. Thus, the particles attach to one another and become a solid through freezing. The overall motion is almost completely lost, as they can only vibrate in place due to the loss of energy.
Alright, so today we're going to talk about some thermochemistry problems. Number 1, suppose we have 100 grams of H2O and it absorbs about 1,255 joules of heat. What is the surrounding temperature change? The specific heat capacity of water is 2.1 GC. Alright, in order to do this, we need to use the temperature change formula, which is the surrounding temperature equals m times c times delta T. Delta T represents the temperature change, C is specific heat, m is mass, and 1255 joules is change. So the problem is asking if we want to find the mass. So we simply just plug in everything, x times 2.1 times 100 equals 1255, and the temperature change is 5.98 C. That's it. Alright, so let's go to the second problem. The second problem says that we need to calculate the amount of heat needed to convert 190 G of liquid water at 18 C to steam at 100 C. Well, in order to do that, we need to go through all phases of state changes in order to go there. So we first start with delta H sublimation, which means turning pretty much, what's that called? Solid to gas, which we're doing ice to vapor. So in order to do this, we just need to put 190 grams of liquid over the molar mass of water, which is 18 G, and that'll give us about 10.54. And then we just simply multiply it by 40.7, which is the constant of delta H sublimation, and that gives us about 42.913 kilojoules. And then finally we just do 429.13 kilojoules plus 190 times 4.18 times 82, which is the other heat change. And that 4.18 comes from delta H fusion, and 82 is 100 minus 18, and that's 82. 190 is the mass. So we just add that to our other one, 429.13, and that gives us our total energy used, which is 494.2544.